Okay, so we should be going live right now. Got it up on my phone in front of me, so I will see here in a few seconds if that's actually the case. Make sure it's picking up my voice too. 1 second here. Come on. Still waiting here. There it goes. It's loading. Alright, looks like we're good to go. Okay, so let me share this around real quick, and then we'll get started. So I'm going to do Facebook. Let's see here. Let's also do Chief Delphi. Oops. I'm doing this on my phone. So that's Chief Delphi. Message this out. Need to do Twitter as well. Come on. My phone is not liking me tonight. Okay. Should be good. Let's pull up the stream on my phone and actually gonna reopen this. There we go. Alright. So I know it says we have 2 people watching them. One of them is me. I don't know if anybody else is watching. I assume that might be my streaming computer. Might count. Alright, well, we'll go ahead and get started. So last time, when we left off, we kind of spun our wheels for basically 2 hours. So, didn't get a whole lot done. But basically what we worked on is this assembly down here with these bearings. Trying to fit these bearings in with the screws for shafts and clear all the flanges and stuff down at this end. And it's really tight. And because I'm trying to design this with machining resources that Stellar Robotics actually has, we don't have really the ability to machine like a solid billet piece that would go down here and kind of solve this problem. We technically could, but if we were actually doing this for an actual robot, it wouldn't be worth probably devoting the machining resources we have to making those parts, when there's probably a way to do it with sheet metal. The problem that we ran into right at the end, that we didn't solve before the end of the video last time, was I neglected to consider that the belt is designed to be tied up against this tube. So like if we look at it from the bottom, this pulley has a belt that wraps around it, and it has to go down like away from the screen, up tight up against this tube here. And basically this bracket's in the way is really what it comes down to. Now this one over here is not. However, we're probably just going to go ahead and change both sides just to make it symmetrical. So I think what we're going to do to start is we're going to get the belt in here so we don't have to worry about like forgetting where the belts run, so they're in the model. And then I think what we're going to do is we're going to try to redesign this bracket a little bit, move the bearings in a bit, and tuck the bracket on the inside of this tube. We still have the issue to consider of exactly like where the rivet heads are going to go. They might just have to kind of, the belt might just have to kind of go over the rivet heads a little bit. The belt is not going to be moving in relation to this tube because the belt is the thing that moves this tube, so the belt will be clamped to this tube or bolted to this tube somehow. So if it's got some small bumps and stuff underneath it, that's okay, like rivet heads, but anything large like this entire bracket is going to be problematic. Alright, so the first thing we're going to do is get the center to center distance here. It's kind of lagging on me a little bit. Alright. So 855 millimeters plus 10 thousandths. Yeah, so alright. And these were 18 tooth pulleys, I believe. Okay, it's been 2 weeks since I've worked on this, so I gotta try to get back into it and remember everything I've done. Yeah. Alright, so what we're gonna do is we're gonna start a new part. I don't model the belt teeth. Typically they don't really factor into the geometry that much. I suppose I could model the belt a little thicker than it needs to be to represent the belt teeth. I'll kind of show what I mean here in a second. Alright, so let's go to this table that I've got pulled up, which is the outside diameter of the pulley, so 27.5 millimeters. So what we're going to do is we're going to make this, so we're going to offset that way. Oops. There we go. And then offset this to the inside. Okay, so now what we're going to do is from here to here is going to be 27.5 millimeters. And then this center to center distance is going to be 855 millimeters. I'm not going to add the 10 thousandths. Actually, yeah, I'm just going to add the 10 thousandths. It'll make our lives a little easier. Okay, this image here. So 2.06 from the outside. That's 2.06 millimeters from the outside. So this is the outside of the teeth of the pulley. Right, so that's the diameter that runs across the tops of all these teeth. So from here to here is 2.06 millimeters, and then the whole tooth is the whole belt, including the teeth, is 3.8 millimeters thick. Yeah. All right. So basically, from this dotted line to here is the teeth of the belt, which we're just going to model solid. We're not going to actually cut the grooves because that would make the model kind of laggy. And then from here to here is the back solid part of the belt. Normally I just don't model the teeth at all, but for the purpose of this, because it's so tight on space in there, I'm going to go ahead and do it. Alright, and then this should be, I'm going to extrude this symmetrically, 9 millimeters wide. And I'll just set the material to rubber. Then we're going to turn on a few, well, just mainly one. We're going to turn on that work plane. And then we're just going to save this, even though this is like a standard part. Yeah, we'll go ahead and throw it in the standard parts folder. The problem with modeling belts and saving to the standard parts folder is you get weird things like this where the shape of the belt depends on what pulleys it's connected to. So what I usually do is something like this. For my naming, I do HTD 5 millimeter, which is the pitch. I say how wide it is, which is 9 millimeters wide in our case. And then I list how many teeth the belt has, which I don't actually remember. I left it up. It's been up and open on my computer this entire time. I think it's this one. Let's see. I'm pretty sure this is it. 1800. So that's can do math. Divided by 5. So 360 teeth. Okay. All right. So it's 360 teeth, and then I say the sizes of the two pulleys that it's going around, because there aren't that many pulley options in FRC. Like, you know, we're kind of limited to either what we can 3D print or what Vex sells. And so there aren't that many pulley choices, and there's also not a ton of belt choices. Now in this case we're not using Vex Pro belts, but so we save all these in the standard parts folder, and then sometimes we can reuse them. I mean, it happens every once in a while. You got to model most of them yourself because there's so many possible combinations, but there's not that many, so it's still worth it to save them in a standard parts folder. If I were to draw a belt that like routed around some complicated set of pulleys, like our turret one from this year, open up our CAD from the 2020 robot. Where is it? Actually, maybe I just didn't CAD the belt at all, or maybe that's just not on this computer. I made this whole sketch to do the calculations for that at some point during the season, to calculate all of the belt paths for the turret with all the idler pulleys and everything that's in that, and it was a pain in the butt. Oh well, okay. I guess I didn't model the belt when I did that. I just had it in a sketch somewhere. Okay, so what we're going to do now is we're going to place this in, and we're going to actually go ahead and place them everywhere they're supposed to be. Oh, standard parts, belts and pulleys, that guy. Alright, now we're going to constrain him up at the top, and then we're just going to, I'll show you how to do this, what I would consider to be the correct way. Alright, so we're going to need one here, one there, and one there. Alright, so for these pulleys, oh right, that was the other thing I was forgetting. I need the mid plane. So I need that. And then I need the same thing, the mid plane for this as well. Like that. Okay, so now what we can do is do a flush constraint between there and there. Just that guy. Okay. And then a flush constraint between that and that. And a flush constraint between that and that. Alright, and then we'll hide these work features after we're done, because it gets really hard to work when you've got all of this like stuff in your face. Okay, so now what we're going to do is we're going to constrain the axis of this end part to some center line here. I think we'll just use the pin, because that's the easiest thing to get to. Same thing back here. And up front. Alright, so now, the only problem that we've got now, I'm actually going to hide this plane so we can actually see what we're doing here. We got a couple people watching. Looks like we're doing okay on bitrate and all that good stuff. Okay, so the problem that we have now is these are kind of under constrained. These are really close. But they do miss. How close are they? 30 thousandths. Alright, so the problem that we have now is these are under constraint, so they can swing out like that. So we gotta constrain that. But that's pretty easy. That's why we have this plane. So there's two ways to do it. You can either do an angular constraint to make it parallel to whatever the plane is between the two axes, or you could just constrain this plane to the center line of this pin. Now, you could constrain like this to here, And see, it doesn't scream at me. Like, I can do that and I don't get any errors. However, you should never do it that way. And the reason is, in this belt model, oops, not the extrusion, the sketch, we added in that plus 10 thousandths here just to make it line up perfectly. However, if you use different preloaded amounts on different parts of your design, like if you did plus 10 thousandths on one, or you didn't do any preload. Most of the time on Stellar we don't do any preload, but because this is a really high load mechanism, there's a lot of force on these belts to do an assembly like this. We're adding the pretension amount. So basically there might be slight differences in your center to center distances. That's the point I'm trying to make here. And so if you constrain it in a way that relies on the center to center distance for the belt end pieces and the actual shafts that you're constraining them to, if it relies on that center to center distance lining up exactly, then you're going to get errors in some cases. However, if you constrain one end and then you constrain this plane to the centerline axis, if there's a few thousandths of difference of the length of the belt versus the center to center distance of your pulleys in your CAD model, it won't give you any errors, and the CAD will be a lot happier with you. So that's the reason you should always do that. However, in this case, because I don't have all the pulleys down here and I really don't want to bother constraining this, I'm just going to do an angular constraint from here for just this plane to like this tube, and just make it 0 inches, and then I'll just do this, all of them, to the same geometry. That's quite a bit. What's going on? I'm an idiot. Alright, it's fine. Okay, so I'm just going to constrain all of these to that same face. Right, and so we haven't made the cutouts down here. I was looking at that going, what did I mess up? But we haven't put that cutout in yet. Alright, so now we can turn off the rest of the planes. We can close out. Oh wait, I want to turn this off as well, just so we don't have 5 million work planes staring us in the face all the time. Okay, so now the belts are in there. So that gives a little bit better idea of where all the interferences are going to be and stuff. So let's open up this bracket. We talked about we needed to tuck this bracket on the inside of that tube to redesign this portion because there's some interferences. I'm not going to edit it. I'm just going to make a new one and just give it a new number, because if we wanted to go back to it, we could. Now, the way I modeled this before, actually, I'm glad I did this. We had this corner relief, if you were watching the live stream last time, to create a sharp internal corner. And then we ended up adding these little notches to clear the bearings on the sides. So we added these little notches here so that these bearings weren't rubbing up against that bracket. However, when we take this and move it to the inside, that's not going to be a concern anymore. So we won't need these notches. However, we will need a sharp corner here. Now, I'm thinking about this, and basically what we're going to have to do is we're going to have to shorten the tube, right, so that these little wings can stick out off the end of the tube, basically, and then we'll just move these brackets down. So let's figure out how I constrain some of this stuff. I think I just mated... Yeah, okay, so that's good, because I mated this this bracket to this bracket, which means that when I move this bracket, these will move with it. Alright, let's figure out... Actually, I have one other measurement. I think this is a 1/2 inch across from here to here. Yeah. Alright, so let's figure out what the... Instead of making the tube shorter, because I don't actually know how much of this tube I want sticking out the top, I'm just going to move the tube. That's spacing, and that is the... Okay, so maximum should be 30.5, and minimum should be 2. Alright, and then what we can do here is figure out which one of these I placed first. It's this one. And I just flushed it to the end. Alright, so what we're going to do here, these are all the same. So what I'm going to do is replace these two. I guess I didn't realize that all these brackets were the same. But yeah, I'm going to replace those two with part 9. And then delete this flush constraint. That allows this to slide out. Oh, I didn't realize this is flushed as well. Okay, so this is flushed to the tube. So I'm going to edit that constraint. And then I'm going to click on the green because I want to redefine the green selection to be this other plate. I want this plate to be flushed to the other plate, not to the tube. So I'm going to click on the green selection, which clears that selection, but it leaves the red one selected. And then I can click whatever I want the new green selection to be. Okay, so now this can like slide. So what I'm going to do, actually I'm going to make the edits to the bracket first. So I'm going to get rid of these notches and then unsuppress this. So, oh, oops. I'm going to just delete that and then unsuppress. But we've got to make this narrower. So this needs to be, we need to subtract a 16th because this is a 16th wall tube. So we need to subtract a 16th from either side. That makes this internally like 0.87, it makes it 0.875 nominally. However, I'm going to take a little more off. I'm going to do 0.875 minus 0.025, which should make it, oops, should make it 0.85 internally. So that's just to give a little extra clearance because if there's a burr on the edge of this, it won't fit in. Okay, so that is okay. Now the other thing is this hole was probably dimensioned, yeah, ½ inch off the side. Delete some of the broken geometry here. Alright, I'm going to delete this dimension and I'm just going to do a vertical constraint from the center of that line just to keep it centered even if we adjust this width again down the road. The other thing too about this bracket is because this part is now not going to be backed by the tube, I'm going to take this hole and get rid of this hole and move it up. But I still want 3 holes, so I'm going to make this whole part of the bracket longer. So I'm going to make this 2 inches instead, and that should just do it, yeah. Alright, so that that's that for that bracket. So now if we go back to our model here, give it an update. Okay, so now that bracket is, oh yeah. How to do this? Right, because I've got to move these to the inside as well. How are these constrained? They're constrained. Oh, right, because this is like a sleeve, isn't it? Oh, no. I didn't think about that. So I've got to get a sleeve that's what, 3/4 of an inch? That's fine. Because I'm going to take off, because it's going from this surface to a 16th off of this. So yeah, a 16th, a 16th. On this side it's an 1/8 times 2. For the other side's a 1/4. So yeah, that means we've got to take this 1 inch standoff, or this 1 inch sleeve, and reduce it down to a 3/4 inch sleeve. Alright, so it's the number 8 spacer aluminum 1/4 inch OD. So let's go to McMaster and let's figure out what part number that is. Alright, spacers, aluminum unthreaded. Come on, load. Alright. 1/4 inch OD, 3/4 inches long. Okay, I'm not going to download the CAD for this because I can just make a copy of this and edit it. But I do need to change this number. So it's 92510, which should be the same, and it's A 467. That's easy. Okay, and then we'll edit this extrusion, make it 0.75, and then we should be able to just do a replace because it's the same part, it's just edited. So I'm going to do that and place this under fasteners. There we go. Alright, so now that's shorter. So we should be able to, we're going to have to figure out these screws too. We're going to have to figure something else out for those, but that's fine. Alright. Okay. I'm just going to clear both of these and then select that face and mate that to the inside. And then do the same on the other side. I could just delete these constraints and redo them from scratch, but I find it a little neater to do it the way I'm doing it here. Okay, and then the other thing we need to do is adjust this flush constraint from the top. Now I picked this first and this second, which is what I want. So I'm going to do 1 inch minus 0.85 divided by 2. And then I'm just going to flush. Oops, I should have done that. Alright. I want this first part to do all the hard work constraining, and then I want this constraint to line up with this part, just to keep it neat. I know it seems kind of maybe overly finicky and a little bit too particular for what we're working on here, but when you're doing really complicated CAD models, it's really good practice to get used to keeping, you know, the order that you do things in really consistent. So instead of having this dimension in here, I'm just going to set that to 0, and then I'm going to clear the green selection and make it flush to that other plate. So now these two plates are just flush to each other. And all of the like hard work dimensioning was done on this plate, and this plate is just constrained to be lined up with this plate. So, okay, so now what I can do is constrain this face to be on the end of the tube. Alright, so now we just have to deal with these bolts, which I think we should be able to just get a bolt that's 1/4 inch shorter. Here to there is, yeah. Okay, so we'll just get the same bolt and just get the one that's 1 1/4 inches, not 1.5 inches. Okay, flat head cap screws, alloy steel, and this is like the stainless steel ones because they were cheaper for some reason. Or maybe they were zinc plated. Zinc plated. 1/4. Zinc plated is considerably cheaper. Alright, so product detail, save. Got it open already. Cut. Fasteners. Alright, so now screw, flathead cap screw. Oh wait, no, we save that for the last. Alright, 832 by 1.25. Flathead cap screw, zinc plated. Then get rid of all this junk. Alright. Now, can open that. Import it, set the material, set the appearance. Come on. And then I have my template set up to create the sketch automatically, so I just delete it just because it's not necessary. Okay. Steel alloy. We're going to do a zinc finish for this. Come on. It's really slow today. Alright, so now we should, in theory, be able to use the replace tool on this, but it might fail. It usually works for imported McMaster components. Like if I have a screw and I import a screw that's a slightly different length, I can usually replace it and it won't break, but it sometimes does. Okay, awesome. Looks like it worked. Okay, so now that should be good. So now the belt can pass through here. It does catch the edge a little bit. There's a little bit of interference, but there's enough deflection in this belt that that's not an issue, because it's like not much at all. It's a few thousandths, I think. 16. That's a bit much, but nothing we can do about it. There's just not enough room to fit this pulley in any other way. So the belt can deflect a little bit. You could even file this with a bit of a chamfer to help the belt kind of not have any tension up against a sharp edge. But the important thing here is that it clears all of this. Like there's nothing hitting the belt with this shaft and these. Now there will be a spacer in here. Oops. There will be a spacer in here. So we're going to have to be really careful about how big that we make that spacer so that it can sit inside the belt. Especially since, well, actually it doesn't really matter that much because the belt will never move in relation to this. When the belt turns, this will come up with it. Alright, so I'm fairly happy with that. We need to figure out how the belt is going to be clamping onto this. Also, I think what we're going to do here, just because we don't need these notches anymore, I'm going to suppress that. And then add. I think I can add fillets here. Yeah. Alright. And then I'm not super worried about the rivet heads, although maybe I should be. We'll come back and look at this later. We might move these holes like up here so the rivet head is kind of just barely on the edge. Actually, one thing I guess I could check. Yeah, so the rivet head is like 0.364, so the rivet head is bigger than this space. If we really wanted to solve the problem, we could use countersunk rivets, which are kind of just their flathead like the screw. You see countersink the hole. We could do that too. I know 971 uses those a lot in their designs. I've never used them before, but they are a thing that exists. Okay, so that's that. We need to find a way to clamp this on. That's the next big thing. I'm kind of thinking, so there's a few different ways we could do it. The easiest way to do it probably is just to have an aluminum plate, just have a couple bolts on either side, have the plate go on the inside of the belt and just tighten it down. That's the easiest way to do it, the most straightforward way to do it. The best way to do it is to have something that actually has teeth on it that engage with the belt teeth, and then do the same thing where you have bolts on either side and clamp it down. That would require 3D printing it, but I don't think that's, particularly unreasonable to do. So I think what we're going to do is we're going to design the part just so I can kind of show you guys how to model the teeth, because it's pretty easy. We'll just use, they're all radiuses and stuff, so you can just use the radiuses from this drawing, so it's really easy. Yeah, so I'm not sure what this dimension is dimensioning, actually. So I'm going to have to look at the way I did this pulley and just double check that I'm actually using the same dimensions, or if I got dimensions from somewhere else. It's been a while, and I made a template before the season started so that we could use it during the build season for these pulleys. So when me and the students were going through and modeling these, we're just basically adjusting tooth counts on a model that we had made from a previous year, like an eye part. Basically, it wasn't an eye part, but yeah. Okay, I'm losing my train of thought here. Let's figure out how long we want to make that. I think we'll just tuck that piece right past the end of this. Although, actually, you know what we could do? We could... I'm thinking we could turn this all into one thing. So instead of having these holes, move the holes to the outside, have the bolt that holds the belt clamp on also hold these on. I don't know how good of an idea that is. That does mean that when you want to take the belt loose, you also take this bearing block loose as well. You would also need, you wouldn't want to put nuts on the inside of this plate. So you wouldn't want to have just this plate bolted in place. You would want to have the bolts go all the way through, just because you'll never be able to get a wrench in here or anything. So if you're going to run the bolts all the way through, you want to be able to tighten them down really good because they're clamping onto this belt, which is how the force is transferred. But if you're going to do that, you really should have a spacer in here that keeps the tube from collapsing. So the question we need to answer is, why is this not... Oh. This is 9, this is 9. Oh, it's only on one side. I have to mirror this. Okay, kind of forgot that I had to do that. But all right. Okay. So yeah, these notches just clear the sharp edge of the tube here. Okay, so what other options do we have? So the other option, we can just rivet it and then have the bolts go over top, but we still probably want the bolts to go all the way through. We could just have the holes here and rivet the clamp plate on, but I don't particularly like the idea of doing that because it doesn't give us any ability to add or remove tension. Like we can't control the clamp force by turning a bolt or loosening a bolt. So yeah, I think we're going to just go with that. We'll put a block in here to act as a spacer, and we'll just kind of live with that design. So let's change the way that we're doing this. So instead of having 2 holes, like 3 holes, we're going to have 2 holes about where these guys are, except here and then down here at the bottom. So let's do this. And this is just a pattern, so we're going to just make it a 2. And I don't think we're going to use number 10s because we just don't have the space for it. So we'll use... Oops, that's not what I wanted to do. Actually, so yeah, we need to go in and delete this constraint, which we just did. Move this off to the side, and we'll... I guess we'll just go ahead and add another one. That. Okay, so we'll constrain this center point to that. Alright, so they're going to be, well, let's start with talking about number 8 screws, which typically have a 177 clearance hole. So I'm going to place a point here and then turn this off from being a center point so it doesn't get picked up by the hole generator. This will be 9 millimeters divided by 2. So that would be what we would need to do. That's not bad. That's okay. So that puts the bolts right on either side of the belt, which is fine. Okay. So now we can make this hole smaller. Let's do 177, which is a fairly standard clearance hole for number 8. We might make the hole smaller. We might go to number 6 bolts or maybe even number 4s, but we'll start with number 8s. Okay, so... And I'm not adding, you'll notice I'm not adding holes in the tube yet. That being said, I'm probably going to need to do that for this, just because of how mission critical they are. Alright, the way I'm going to do this is I'm going to put a sketch on the side. I'm actually going to use adaptive geometry for this. So I'm going to project the holes from this plate. Project each of these holes. Now, I turned on construction geometry, so these are construction geometry. Then I'm going to place center points. This kind of decouples the adaptive geometry, which are these circles, which you can't edit because they're projected. This kind of decouples the whole geometry from the actual projected geometry. So all the projected geometry is used for is the location, but the actual hole itself is defined by this hole feature that we're about to create. We'll go all the way through. Yep, and it remembers the last hole size, which we'll keep the same for now. All right, then if we go back, you can see the holes line up perfectly. And then if we like move this part, well, the whole tube moves, but if we move this part, like if I adjust this mate to be like 0.2 or something, and they move out, so that moves this plate. Come on. So now you can see, it's kind of hard to see, but I added a gap between these plates and the end of the tube. So if I go up here and I look, the holes still line up. So if I get rid of that gap again, it moves the tube out and it updates the holes. So you don't even see them move because they always stay lined up. Okay, so that's that. So now we need to model this little like clamp plate in here. We don't have a ton of room. We've got to be careful because it's going to stick up a bit because we're going to want it to be fairly bulky just to have the strength. So I think we're going to have to make sure that it's a little shorter. So the distance from here to here in the Y direction is 1/2 inch exactly, because this is 1/4 inch to the edge of the bearing and then 1/4 inch to the hole. So because the 1/2 inch diameter on this bearing. So from the edge of this bearing to this hole is 1/4 inch, so we're going to want to make sure it's a little less than that from the edge of this like clamp block to the center of the hole. That's not a super great explanation, but it'll make a little more sense. So that's 1/2 inch. So we're going to be able to go like 1 inch long. We might extend it out a little bit longer on this side. There won't be any bolt holes there, but I don't know if that's really a problem. So let's do a clamp block that is 1 inch. Well, we'll make it a little extra long. We'll make it 1 inch wide. Okay, and then we're going to extrude this out to be kind of thick. Actually, no, we'll stick with 1/4 inch. I don't know how much space we're going to have. We don't need that anymore. Okay, so now what we're going to do is create a sketch here on the bottom. Oh, and I need this to look at what dimensions I used there. Don't need the assembly. So that's the offset one. Okay, so we just used 3.05 and 0.86. Which is taken off of this drawing. So this is 0.43. So yeah, 0.86 diameter. Oops. What am I doing here? There we go. Okay, so what we're going to do is we're going to do the same thing. Oh, I see how I did it. Okay. All right. Well, we can do that the same way. So what we're going to do is we're going to project that. And we're going to make this all construction. And we're going to make a line that goes across here. Oops, that should have been construction 2. Then that should be 2.06 millimeters off from the bottom. So that'll represent like this inside circle, because we're basically taking this geometry and flattening it out. So 0.035 millimeters, or 3.05 millimeters, sorry, like that. This should all be construction. 0.86 millimeters, and that'll be equal in size to that. Okay, so this needs to be tangent to... Nope. Come on. Alright, that needs to be tangent to that. And then these need to be tangent to that and the big circle. This needs to be over there. Okay, that's fairly reasonable. I think we're going to put this tooth like right here in the middle. I'm going to try that first. We'll see how that works. We might shift this around a bit. Alright, so from there to there. I'm just using center point arcs to connect all this stuff. And then we're going to take a line and we're going to close off the profile so that we can actually extrude this. Okay, so we're going to extrude it through all. It automatically switches it to cut. Alright, so then we'll take that feature and pattern it down that way every 5 millimeters. Actually, wait. We're going to do one thing before we do this. I forgot to mention this. Right. How am I going to do this? It's a little more complicated because I'm like missing part of the geometry. So I guess what I'll do... I can't do it that way. Okay. So, yeah, see, it only wants to select the construction geometry. It's so annoying. Oh, there it goes. Okay, that's what I wanted. I want it to... Alright, never mind. I'm just going to do this myself. Okay, and I'll explain the purpose of this here in a second. Okay, there to there, and there to there. And then I'm going to take this all the way down to the end. Make this tangent to that. And then bring this down to that end as well. I don't think this got the... Oh, it already did it. Okay. Then this should be tangent to this line as well. Why will that over... Oh, right, because it has to be. No. So what needs to be is this needs to be constrained to that. Okay, so then what we can do is we can define an offset here, and the offset's going to be really small, like 5 thousandths. And then this can be just like whatever. It doesn't matter. Do it that way. Okay, so then what we can do is share this sketch. So basically, what this allows us to do is it allows us to perform a contraction on the tooth geometry. So basically make the 3D printed part teeth smaller in every direction than the actual true ideal tooth geometry. So, and the reason that I'm modeling it this way, and I really didn't need to model it this way for the purpose of this like design exercise, because we're not actually going to 3D print this part. However, for Stellar's 3D printer, this just modeled the way it is, printed just fine. However, for one of our students' 3D printers, who did our Stellar's 3D printer crapped out in the middle of the season, and one of our students did most of our 3D printing, and his 3D printer printed everything a little bit oversized, and so the pulleys didn't fit well. So we kind of cut a bunch of material off the tooth, and then they worked perfectly. So when we model our pulleys, we model them both ways, so that we can kind of just do a different. We can turn features on or off and do a different export of the STL, and then we have the ability to print like contracted teeth or the ideal tooth geometry, depending on which printer we're using. And typically we just do a save as, and we make a separate part, one that's contracted, one that's not, which is why this one says like contracted in the file name. And the way to look at what this tooth looks like here, we just did an offset. This was easy because we just did an offset because we had the full tooth geometry. I couldn't do that here, which is why I had to like remodel all this geometry because half of it's gone. I can't just project it and offset. Long story short, it kind of doesn't matter because we're not going to make this. Oops. But I'm going to go ahead and do this contracted geometry just because I think it's probably good to have that ability. Now we're going to do our rectangular pattern of both of these extrusions. So pattern it that way, 5 millimeters, and maybe 10 of them. Looks like I only need like 7. That's what I was afraid of. Alright, okay, so I guess we're going to have to move this then. Inventor has that weird thing where it's like, it doesn't redo the extrusion, it only redoes the effect, like it doesn't pattern the extrusion itself, it patterns the effects of the extrusion. Which is, I hate that it does that, but that's the way it works. So what we're going to do, instead of constraining this on the edge like this, we could do some stuff to solve that problem, but I'm just not going to bother. We're just going to move this so that that's right there like that, and then it should work fine. There it goes. Okay. So now what we can do, if we absolutely want the tooth on the edge of the part, we can just cut the end of the part off. I don't know if it matters. This will get printed probably in this orientation. So the printer will basically just put like a single strip of plastic down this side because this is so thin. Like from there to there's 12,000, so it'll lay like one bead of plastic. It might not even pick it up in the slicer. I really don't know. Okay, so what we're going to do now, just because I want this to end up being like an even number of teeth. Oops, sketch, not feature. We're going to do, what is that? 1.25 divided by 0.254. Oh, wait. 0.254. What am I trying to do here? 10 divided by 25. That's what I'm trying to do. No, 5. I can't do math today. Alright, 0.1965. 1.25 divided by that is 6.35. So I think we'll do there we go. Oh. Yeah, I should have done this a little differently. No, like that. No, like the center point that's there. Oh my gosh. There we go. Okay, so now I can move all this over, and what I should actually do is dimension this to 2.5 millimeters. And then this line really should not be connected here. And I'm getting a call from an 855 number. Not going to answer it. So if you're somebody who is calling me right now, I am sorry. Okay, so that should be like that. And tangent. And then I'll just make this collinear with that. Okay. So now these are like centered. So that's actually quite a bit better. That looks more like it should. Okay. I'm more happy with that. So give this a save. Now we can put our holes. So we'll start on this end. Now, this end over here, we're not going to, I'm going to do a 0.5. Actually, I can't remember what spacing was. 0.531, right, because it's based on the metric belt width and the hole size, so it's something weird. No. So this will be 0.531. This should be construction. Point at each of the corners. Snap that onto there. Okay, so horizontal constraint from the center point to the center point this way, so it's constrained vertically, but it can move horizontally. Then from here to the edge of the part, you remember we said this needed to be less than 0.25 so that the edge of this part doesn't like rub on the bearing. So we'll go like 0.23. Like it doesn't need to be much, just needs to be a little bit of clearance. I'll make that construction just to match. And these holes, 177, and then just go through the tooth profile. That's fine. We could like trim the tooth profile so it's only in the middle where the belt is, but I think it's probably better to have it go across the whole width for strength. We'll set the material to ABS, and we'll set the material to blue because that's the color of filament we usually use. Let's see what this looks like with fillets on the corners. Yeah, we'll go ahead and do that. This will create kind of some weird stuff after the print, but you can just trim that off with a utility knife or even just a file. Okay, so, oh, we should do, nah, never mind. Okay, so once by the z-axis, once by the x. Okay, so now we can do a couple of things. So 2.06, 3.8. So 1.74 is the distance from here to here. So that's the distance from the tops of these teeth to the back side of the belt. Actually, we'll constrain it to the tube because technically that's where the back side of the belt will be because it'll have to deflect some. So 1.74 millimeters. And then actually we'll just do a constraint from this hole to that hole. And then we just need to keep it from rotating. So I'll do a angular constraint like that. Okay, so now there's not actually any teeth in the belt. Wait, what? Oh, yeah, and so this is not correct. Like this, there's a gap here because the belt interferes with the tube a little bit, but in real life this would just deflect a little bit and to be on top of the tube, and then that gap wouldn't be there. So that's not really an issue. Okay, so the only other thing we need is a block to go in here, which will be 3/4 of an inch and probably 850 tall with those same bolt pattern. So we'll make a block that is an inch long, 0.85 tall, and 3/4 of an inch in this direction. It'll be tight in this direction, but that's what we want. Like, we don't want slop in the width. So if you have to like sand it down a little bit to get it to actually fit in the tube, that's okay, but you want it to be a pretty snug fit, so you can't really afford to make this particularly undersized in that direction. Alright, so then we just need to put this whole pattern in. I'm just going to center it because we're not at risk of interfering with anything. So 0.5 and 0.531. Okay, and the holes, now for this is a 3D printed part, so I'll oversize the holes by 20 thousandths because they shrink. Go ahead and fillet the corners. Oops. Like that. Okay, give it the next number in the series. Drop in the assembly, and we got to figure out what we need to do next. Once by the Z, once by the X. And I'm going to use the insert to line this hole up. That one. And then it just needs some sort of angular constraint. Don't go the other way. Dang it, come on. I'm just trying to get to swing up. There we go. Okay, I just wanted to be able to select this face. Do like that. Okay, so that piece is in there now. Yeah, okay. We're not going to put the bolts in because I'm not super worried about it. You just use button heads. I guess I should probably check what the length is, but 832 bolts are super easy to cut, so I wouldn't really be too worried about the length here. I'd be a little concerned about like a nut fitting here, but it should be okay, and there's enough room to get a wrench on it. You would pre-assemble this before you dropped it down in. You'd probably get the belt on, just have it loose. We'll talk about assembly a little bit, like once the design is done, and just kind of check to make sure we can actually assemble it. So like a 1.5 inch button head would be probably sufficient. You could use the low profile nylock nuts and be okay. Alright, I'm pretty happy with that. It's very, very tight. Like it's just, there's just no room in here. So that's about as good as it's going to get. So that is pretty much done. I'm kind of wondering if we've got some interferences here that we didn't foresee. So I'm going to turn all this stuff back on. Do we have a slight bit of interference here, but once again, the belt can deflect a little bit to handle this. And plus, this belt needs to clamp to this piece. So actually, what I'm kind of thinking we're going to do, so like this belt clamps to this piece down at the bottom. This is actually a bit of an issue here. How are we going to fix that? Because like this will just not work. Like you'll go to tighten these screws down and it just won't go. We might need to just, no, that won't work. We can't just notch it because this moves up. We might need to adjust these blocks and just move this one out. Oops. This is going to be an issue over here too. But the problem is if we move this out, that means that it's going to interfere worse here. Well, one easy way to solve this problem is just tweak the outside dimensions of these stages, which we might just go ahead and do. What size is this? 3.5. Yeah. I kind of like them being nice round numbers, like being quarter-inch increments, but I think we're going to have to go to like some weird number, which really sucks for making everything line up nicely with fractional hardware, but probably what we need to do. So if we're going to do it that way, we really should do it here too and just make all this stuff like perfectly exact is really what we should do. So we only need like a very tiny amount. So from that is 0.610, 0.1220, and we've got like 1. Yeah, 188. So we need, it's actually it's 1.875. So it's we need to go from 1.22 minus 1.185. So we need to add 33 thousandths to each stage. That really sucks that it's such a small number. But so that means we're going to add like 90 thousandths to this outside one. All right, we don't really have much choice, so let's go ahead and do that. It's that is, oh right, so it's 0.625. Let's close some of this stuff. We gotta adjust the stage spacing because that's how this is dimensioned. So it's 0.625 on either side. Oh right, because it's plus 0.625. So 6.5. We'll just call it 658. Just round up. Alright, and then we've got to edit this flange. Okay, and then this here is clearance for the material thickness, so it's not 0.625, it's 0.0625, so that's dimensioning something else, so we don't need to change that. Okay, so now this has dimensions on it. These need to be 0.658. Oops. Typed 625 out of habit. Okay, let's open this up and let's basically do the same thing where we change all the 0.625s to 0.658s. Oh, we gotta figure out what this number is too. So it should be just to the top here, right? So 2.316. 316, 58, 58. All right. And then same thing here. 316, 58. Good. Don't need that anymore. And this should be from there to there is 632. 632, 658, 658. All right, and then 632, 658. All right, then we need to adjust stage spacings for this as well. Keep typing that out of habit. And then should be this one. There we go. Okay, let's collapse that all the way down. Give that a save. Alright. Alright, so now this is tight. Or I guess there's a small gap because we kind of added in a little bit of extra space. Yeah, there's like a few thousandths, but that's great, that's fine. So now, down at this bottom end, instead of this having to like deflect out of the way of the end of the tube, now it'll be like stretched down to it, but like it's such a tiny amount, it's really not gonna move that much at all. Alright, so it's a much better fit. It means that our stage sizes are super weird now, but it's still like slightly under 5 inches, so it's kind of convenient that way. Okay. Alright, so now we need to figure out what we need to do next. So basically what needs to happen to finish this design is a few things. We've got to take the notch designs and propagate them to the other stages. We've got to do bottom rollers, so like we've got to basically do the same thing that we did here, except on the outside of this stage to roll on this, and then same thing on the bottom of this stage to roll on the inside of that. We've got to do the bearing assemblies up here at the top, just like this, except out here. So let's go ahead and get the notches in there, because that's kind of been, these old designs have been kind of hanging around, and I would like to get those taken care of so we don't forget. And then at the same time, we're also going to go ahead and put the notch down at the bottom like this. So let's open up this part, and we'll close these and open them in order. So we'll do this one. So basically what needs to happen is figure out where we started this. I believe it's the first cut. So we just going to open this assembly. 1.75, 1.375. Yeah. And this was centered too, which is not how it's supposed to be. So delete that. Put this point in the middle. Oh, right, but it's not that. It's oh, and it's something weird now too, isn't it? Actually, we gotta adjust this too, don't we? So it's, you know what? No, we're gonna do this a little differently. Even on this part here. So we're gonna delete that dimension. Come on. I keep hitting the wrong key. There we go. Alright, so we're gonna delete that dimension. We're gonna grab a line out here. We're going to mention from here to there, which is 16th, because this represents the material thickness. Then we're just going to use the center point of this line to locate this point. It's like a much cleaner way to do that. And then I just need to know, did I line the bottom one up with this, or did I dimension it separately? I dimensioned it separately, so we'll do it the same way down here. Delete that dimension, grab a construction line, offset at the material thickness, and then just use the center point. Okay. Okay, so we're going to do the same thing here. And the nice thing is we don't need to know what this outside distance is, because now it's something weird, right? It's something not fractional, because we went and changed all those stage spacings and dimensions, so it's going to be hard to keep track of. So this means that we will never, unless we change the material thickness, which we're not going to do. So unless we change the material thickness, we'll never have to. Why is it freaking out? Oh, didn't delete the dimension. Okay, so and it's 1 point. Oh. 1.375. And then we connected those. That was not real geometry. Should have been real geometry. That was it. Okay, so now cut, profile, add the extra bit, and we gotta go fix all the things. Alright, so this cut, I can't remember what I did for that here. I just dimensioned up from the bottom. We'll see if we'll see if it's D47 for this part as well. it is not. It's fine. Just it's just this dimension, D48. All right. Okay, and then we're gonna delete out that broken point as well. Okay, and then holes. I think I just used. Oh, no, I just did the same thing. Okay, so then I gotta replace that dimension like so. Line down to there. D48 divided by 2. Oh, and make that line aligned with the axis. Okay, so that's that taken care of, and then we just need to do the same thing down at the bottom, except instead of dimensioning the center of that like rectangle, 1 3/8 from the top, we'll just dimension it the like center to center distance for the, like if you look at this here, we got to make this big dimension across the top, the center to center distance for the belts. So that is 855 millimeters plus 10 thousandths of an inch. So we're gonna throw that in there like that and do 1.75 and 0.7. And then actually I'm going to do this a little differently than I did on the other one, because this is probably how I should have done it anyways. I'm just going to do a collinear constraint between that and that. That way we don't have to do that whole like dimension thing for a 16th. It's just less dimensions in the part. Alright, so project those, connect them with a line, then dimension from that line down to here. Make this 855 millimeters plus 0.01. Then project. Is that how this one is too? No. Are these different lengths? I think I ended up making this one taller because it had to clear the bearings. I don't think that'll be an issue though. We will find out. Alright, cut, yes. New sketch. Now, oh right, I needed to figure out what dimension that was. D71. So now for this, do D71 divided by 2, then attach so. Okay, and then basically same thing for the whole pattern. There's a lot of repetition. We could do this one more time. So D71 divided by 2. And then what was the whole pattern? 3/16 of an inch off the inside and 5/8 tall. So 0.625, and that's it. And then dimension from here to there, 3/16. And then these are 0.196 holes. Alright, so that's that. And then that should give us... Oh right, we're going to use this one over here though. Something's not quite right. Just needed refreshed. Oh right, because we moved this, so all this stuff had to shift around. All right, let's do that on the outer stage parts, and then we can move on with our lives. Do something else. Okay, so the first thing we got to do is deuce that out. Constrain to there. Like that. Just make that not construction. Construction geometry stayed on. Alright, so that's just how that works. Okay, make that 1.75. Okay, that's going to start screaming at me as soon as I do these cuts. As soon as you can start doing this stuff, like once you do it once, if you can memorize the dimensions, it goes way faster because you don't have to keep flipping back and forth. Although I did forget to measure, or to check D47. Alright. So, delete that point, grab that line there. D47 divided by 2. Make that aligned vertically. And do the same thing for the whole feature. Oops. Of all the points I could have picked, I picked the center point. Alright, D47 divided by 2. Alright, so it goes a lot faster when you don't have to keep flipping back and forth between the two parts and looking at different sketches to measure dimensions. Alright, so for this guy, like I said, what we're going to do here, it's just same thing. Project that. Oops, should have done that. So, and then this dimension between the center points, I forgot to do this. Eight 855 millimeters plus 0.01 inches. Close that out. Keep forgetting to turn off construction before I place those. Okay. And, oh, I did want to check what dimension number that was. D70. Okay. So now, from there, D70 divided by 2, and center point 255, 1.52. Come on. Do the cut. Like I said before in one of the previous videos, you could do this like sideways rectangle in the same sketch as you did that one. Honestly, it's probably the better way to do it, but I started doing it that way, and I'd rather keep them all the same than optimize the way that I'm modeling this particular feature. It also keeps the sketches a little cleaner. D70 divided by 2. Okay. Alright. I'm going to check. Yeah. Alright. Okay, give that an update, let all that stuff move where it needs to go. Let's work on, oh no. Yeah, that's the other problem. Is when you start start messing with the stage spacing here, you can't use these same length of bolts anymore. I hadn't thought of that. All right, so from there to there, so we're using 2.5. So we could, oh man, so we can go up to 2 3/4, but they're going to stick way out. That isn't that big of an issue though, because there's nothing to interfere with up here. So, I don't know. That might be worth doing. I'm not going to mess with that right now, though. Okay, so basically up here, this is a lot easier just because oh, that was the other thing, too. So probably going to have to do the similar cut to all of these and propagate that out as well. We'll cross that bridge when we come to it. Okay, so this is going to be a little bit easier on this stage than it was on this stage, just because there's not really an issue of interfering, of having these pieces. Basically, the bearings going crossways this way are going to be at the top, and then these are going to be down at the bottom, and so there won't be a chance of interference there. Also, I realized why those are closer to the bottom. So really what we should do, I think it's 375. Yeah, so that's 1.875, and this should be 1.5. Yeah, okay, so for these two parts, that top feature should be shifted up. So this dimension should just be 1. And then that pulls this up from the bottom like it was on the other part. So that's how it should be. It's not super critical, it doesn't really matter that much, but just for consistency, that makes all the bottoms the same. So all the bottoms are the same, but the top of this one is different because we had to make this a little longer to be able to support these shafts. But we don't have to do it on these other two stages because there's enough room beside these blocks to put the bearings for this side of the stage above it. Okay, so really not a whole lot. What's going on here now? Why are these not centered? Hold on, let's fix this. Oh, it's probably the same thing. Yeah. So I think what we'll do, cross here from the top, because I don't want to put a line over top of that, so I'm not going to do exactly the same thing. I'm just going to do like that. Okay, so that shouldn't be an issue in this direction. Actually, probably will be. Wait, so from here to there is the full width. Why did I do it this way? Alright, I'm just going to delete that and make my own. So now I have access to the center point of the full width, so then I can just put a point here, make it not a center point so the whole feature doesn't pick it up, go from here to here, actually delete, actually no, I'm going to make that. Yeah, like that. Okay, that should be in the correct spot. So now mirrored that hole. The origin. So from here to Okay. So that's fixed. That's something to keep in mind. Moves all that stuff around back to where it's supposed to be, and it still doesn't line up. What the heck is going on here? 658, 658. Why are we not? I'm confused. Okay, so 625 there. 658 there. $625 there. And wait, is it the same for all the rest of these? 658. I think I screwed something up on my math. So I was doing point. So I think what I needed to do, I'm kind of shooting in the dark here now at this point, which is kind of obnoxious. I think what I actually needed to happen was this needed to be, actually, real quick, I'm about to go through and redo all of these. That's obnoxious. Okay, we're adding 33. So what needs to happen is this needs to be 625, 625, 033, and then this is 283. So I need to do the same thing here. Well, this is actually okay. This is fine. That's just why I guess it's right in that direction, maybe. Oh, wait. Oh. I wish this dialog box could get bigger. Alright. So that'll be 625. And then 0.033. Oops. So now this stage should be correct. No? Oh, right, I've got to, yeah. I've got to make this 0.625 plus 0.033 divided by 2. I'll just copy the text there. Go like that. So now 642 and 642. Okay, so alright, that's relatively painless. I can carry that across to, I do need this dimension though. It's 2.283. Okay. So 2.283. So basically what happened, if I was just going a million miles an hour there and you guys weren't really following, basically what I did there was I added 33 thousandths to either side, but I was supposed to add 33 thousandths overall. So just the way I did it made it a pain in the butt to change, but it's fixed now. Okay. That was supposed to be 0.033. Okay. And then this is the one that's kind of a pain in the butt to change. So 283, 625. Plus 0.033. And then update and copy the text there. Actually, just gonna, oh, I gotta hit enter. Just do all of them, so I don't have to do any more. So that's all of them, including the ones for that stage. Alright, so I want to know what the dimension of that stage is. 3.566. So now I should be able to measure on all 4 sides of all 3 stages, and it should be all the same. Which I'm just going to do all pairs just because I should have done it earlier. I think I already did this one. Okay, alright. So now we're perfectly good and perfectly concentric, and that brings our overall size to 4.849. Okay, so let's turn off visibility on that stage. Actually, no. Let's kind of get that stuff out of the way. Let's go ahead and put the pulley and stuff in here. So how did I do this last time? Dowel first? No. Blocks on the inside first. Then blocks on the outside. Then dowel. Then that. Okay. And blocks on the inside are part number 6. Alright. Then insert. And blocks on the outside. Flip around. Okay, like so. Alright, so now the dowel, which I don't actually remember what, I think it was the 1.5" one. Yeah. Standard parts. Fasteners. That guy there. So this was constrained to that. And then we just did a gap from there to find, kind of like peek in at just the right angle. Select that face there, offset of 10,000, so it's even on both sides. And then back to this folder for the assembly. Constrain that to that. And then what was the offset? 0.035. There. Okay, so that one's done. So now we got to do one down on the bottom of this stage. So we'll turn off visibility on that guy and basically just repeat that whole process. Bottoms and the dowel pin. Peek in and get the offset taken care of. And then the pulley assembly. I'm going to flip it around just for consistency. Oops. Mashed a bunch of keys there. And I'm just going to measure just to double check. Yeah. Okay, so that is all of the pulleys, all of the notches, outside dimensions, all that stuff taken care of. We still do probably need to like trim these flanges, which I guess we could just go ahead and do. Might as well do it while we're kind of on the roll of carrying changes from this top one downwards. Turn on the visibility there. Okay, so I think we're going to finish this, then we'll probably just end the stream there. My voice is starting to get tired. Where's that feature? I think it's just face, corner round. Where's the cut? Or did I just shorten the flange? I bet I just shortened the flange. 0.75 minus 0.2. Let's just do that. Let's open those. Do the same thing to each of these parts here. Yeah. Ah, shoot. I copied it to the clipboard and then hit Control C instead of Control V. So I copied the one that was already in there. Okay, so now the issue. Oh. What was the deal here? We just moved the holes. That was what it was. Did we do that? Actually, do these line up? Did we do that? Yeah, they do. Okay, so from here to there is 375, but on these it's ½ an inch. I forgot that we had moved those holes. Okay, so that's easy enough to do. This needs to be like that. Same thing there. And on this part as well. So this whole operation that we're doing here is pretty typical for doing CAD design. I am sure, I mean, I only have my own experience to base off of, but I'm sure that every other CAD designer out there in FRC is doing the similar thing to what we're doing here, where you make mistakes, you got to go back and change stuff, you got to add a little space, you know, make a cut here, add a hole here, move stuff around. That's just how design works. So what we're doing here is a fairly representative process of how you go about designing an FRC robot and the types of changes you have to make. So, you know, I'm very particular about where I put my dimensions, what geometry I attach to. I add construction lines in certain places and I don't in others. And I'm very particular about the way that I set all that stuff up. And to a certain extent, that's a toolkit that I've kind of just developed for myself with, you know, my years of experience. And every designer has to kind of come up with their own conventions when they're working on their own stuff. It's a little bit, you got to be a little bit standardized. So if you're working on a project with other engineers, you're not doing things completely differently, but the big thing is just to keep things consistent and to make your sketches and your features and your dimensions and all that stuff in a way that allows you to go back and make the kind of edits that we're doing when you screw something up and you need to make changes to the design. Because you will have to make changes to the design. There's nothing wrong with that, but you just need to make sure that everything's modeled in such a way that it's not completely unfeasible and you don't have to go in and like delete parts and design them from scratch. You can just go in and make edits like we've been doing to this project. So I'm not claiming that the way that I do it is necessarily the best way to do it, but it is a way that works. And so you got to find what works best for you and what works best, you know, in the group that you're working with if you're CADing something with more than one person. Okay, so this little bulge here is for the bolt hole, not for the rivet hole. So we won't be able to add that until we add the rivet hole. But my voice is getting a little tired, so I think we're going to end the stream here. Next time, we're on a good track. We kind of got caught back up to where we're actually making progress. We didn't get a ton of visible stuff done, but we did get all these slots put in there. We got the pulley put in there. We got this thing in here taken care of, which is probably one of the hardest parts of the whole design is this bearing assembly down here. So that's done. It looks like it's going to work now. We got the little clamp block designed. We eliminated some of the interference with our belts. So yeah, we made important progress, although maybe not super visible progress. So basically what we have left to do is we've got the bearings at the top up here on this stage and this stage, which should be pretty straightforward. It's just this. We just got to throw some holes in and put the parts in. Down at the bottom, we've got to do bearings as well. Not 100% sure how we're going to do it, but we've got a little more room than we did down here, so we can be a little bit more flexible. But we're going to have to add the bearings down at the bottom for this stage and this stage. And then after that, the only thing that we have left to do is drive this whole thing. So I think we might change the way this pulley is done, or we'll add something on the side here where this goes around an idler, comes up around a drive pulley, and then comes back down. Either that, or we might just call it. I don't know. We've been working on this project for a while. We might not actually put a gearbox in there. We might find some other way to kind of show that. I don't know. We'll see. We'll see how long the other stuff takes. I don't want to be working on this for another month or two, but yeah. Okay. Well, thank you for watching. That'll be all for now. I'll make posts on, the usual places: Chief Delphi, Facebook, Twitter. There's only 3 viewers at the moment, so I don't know who's on here. It's probably one of my students. If you're not one of my students, thanks for sticking with it. Thanks for watching. Yeah, if you're watching this on the VOD on the Stellar YouTube channel, thanks for checking it out. Check out our other CAD videos. We've got a whole bunch of stuff from our CAD class from a couple of years ago where we kind of do the same kind of thing we're doing here. We do little projects. They're a little simpler, though. They're a little bit more organized, where we're not going back and changing stuff all the time. So check those out, and I will see you guys next time.